screen?
Yes, we do.
Okay, then. Okay, then I start. Also my name is Karsten Einwich. I am from COSEDA Technologies. We are a company which provides system-level tools for modeling, simulation, verification based on SystemC and SystemC AMS. I myself have also research career before. I worked 20 years for Fraunhofer before we founded 5 years ago COSEDA Technologies. Today I will present some activity we had on customer request on doing static analysis of SystemC AMS architectural level, concept level models. Okay, what's the outline of my talk? I will give a short motivation, explain the generic concept of the static analyzer, show how this framework is implemented in SystemC, give an example for a very simple analyzer, show some application examples of this analyzer, and give some further outlook how you can also visualize the results of the analyzer. Then, what's the motivation? If you're doing system level design, concept design in the early phases, then a lot of properties, a lot of performance parameters can be analyzed and estimated statically using at the end the structure of your system, and you can use very simple formulas. Also maybe a simple analysis is a power analysis. You have certain blocks and different hierarchy levels, and what you usually do, you estimate the power of your submodules and you simply sum it and propagate it through the hierarchy. Then. Static analysis is usually extremely fast because you have to do only simple operations to do so. It's usually much faster than dynamic analysis, especially if you may be considering in the analog domain and noise analysis, which takes a lot of simulation time, but in static static estimation of the noise is a simple sum of the noise power. So that's you can do an extremely fast simulation compared to doing it in the dynamic sheet. What we saw at customer sites is that very often for static analysis, complex Excel sheet were used, especially for RF designers. It's a common practice that they have very complex Excel sheets to calculating or estimating performance parameters. What we see more and more is that it's very difficult to maintain consistency between the Excel sheets and the later implementation or also the system level model. Then. And what also becomes more and more hard is to managing different configurations of the systems. Also a lot of mixed signal systems becoming more and more configurable so that you have a lot of different register settings, different gain settings, different signal path settings. Usually in Excel sheet, you have for each setting then a different tab in your your Excel sheet. But if you have then several tens or hundred configurations, then this becomes somewhat cumbersome. Then. And what we see also more and more that the structure of the system becomes more complex. Also especially if you maybe do a gain analysis, in former times you have a simple signal path, but nowadays the passes have branches and sub-branches, so that becomes much harder to represent that calculation inside the Excel sheet. Examples for static analysis I mentioned before, power consumption, maybe power consumption in different operating modes. What you could also do in a similar way is estimating the chip area. If you simply add a property to each module, what you estimate how big it could be. Timing analysis, static timing analysis, and then more in the analog domain, gain analysis, signal level analysis, noise analysis, or in the RF domain, there is the so-called interception point, which is a measure of the nonlinearity of the system. Those are typical examples which you can statically analyze. Yeah, what is the challenges to make especially we as a tool vendor, to make a generalized static analyzer? The challenge is that you have numerous application, and the analyzers are usually or very often application specific, and you have customer specific use cases. Especially, as we know it from the RF domain, there are usually no commonly agreed formulas to calculate certain properties. So that usually each designer has its own way how to calculate certain properties of the system. Then, so that was our goal, to create an easily extendable framework. But at the other side, we would take away from the people all this nasty stuff like setting up the data flow graph, setting up the hierarchy tree. This stuff we wanted to abstract. Yeah, and creating at the end, our goal was that creating a new analyzer, a new application-specific analyzer, should be minimized to only providing the formulas. Yeah, what is the generic concept or the main idea? That means, okay, we wanted to attach properties to the modules, to SystemC AMS based modules, and then afterwards we wanted to analyze this property using the hierarchical information of the SystemC AMS models. That means using the structure and the connectivity of the model. So that's at the end, we have a kind of shadow model which implements for a certain static analyzer the property of the system. Then, how we can map this concept to SystemC. SystemC has a concept, it's called SC attribute. Attributes can be attached to any SystemC object. An attribute consists of a name, which is a string, and a value, which is an arbitrary data object. And our static analyzer is based on this attribute we derive from this classical SystemC attribute, and restrict the objects where we can attach this attribute to SC modules. So that means our generic or base attributes for the static analyzer must always be attached to an class of SC core, SC module. And what we also doing then, we are automatically referencing the ports of the corresponding module. On this way, then we later on can set up analysis like a data flow analysis. And yeah, after these attributes are attached, we can use it for an analyzing. And that means for the analysis, we're using the SystemC hierarchy exploration capabilities. That means SystemC has a method to get all top level objects. And from each object, you can also get parent objects. And on this way, we can collect all attached attributes and can also using the structural information for the analysis. Yeah, principally then, each of our static property of our base attribute will have a callback method, which describes how the attribute is propagated through the calculation. So then, after we have attached the attribute, we need a kind of analyzer, and generically our analyzer supports, or we detected that there are maybe three base types of analyzers. One is a hierarchic analyzers. This uses the hierarchy for calculating the property. Typical examples are the power analyzer, where you have to sum at one hierarchy level all attributes and propagate it to the next hierarchy level, and then sum again to and propagate to the next hierarchy level at the end the power. Then a second category of analyzers will be data flow analyzers. Typical stuff is if you want to analyze a signal path, therefore you have to set up an data flow graph. As a typical examples are, if you want to analyze the gain, then you start at the starting point at the source, and you have the first module which has a certain gain, the second with a certain gain, and then you have simply to multiply the gains to get the final gain. And there is a third category which we not yet implemented. It's an equation system-based analyzer. In this case, each attribute will contribute to an equation system, and afterwards you have to solve this equation systems. Examples could be calculating a settled value, or an AC analysis could be also an example for an equation-based analyzer. This is currently not required because SystemC AMS has an built-in AC analysis, and so that we currently focus on the first two categories of analyzers. Yeah, how this analyzers is technically implemented. Implemented in this SystemC. That means we have a base class for our analyzer attributes. This is called COS analyzer attribute base, which is, how I mentioned before, derived from the SystemC standard SC attribute. And the most important function is this callback function, value function, which the user, or which if you implement a concrete analyzer, has to be implemented to provide your formulas how to calculate from the previous value to the propagated value. And then there are some utility functions to accessing to the imports and outputs for this attributes. That's why this attribute has to reference automatically the ports of the corresponding system. And secondly, we have a base class for an analyzer. The important function is the callback function analyze, which from concrete analyzer has to be implemented. And then we have different utility function. One is analyze the data path. This function will represent a data flow analyzer and will setting up the data flow graph from starting points and call automatically the value function of each attribute, so that the data flow graph is or the properties are calculated. And the second possibility is analyze hierarchy. In this case, an hierarchy tree is set up, and automatically the value function is called through the hierarchy. And then okay, we have two utility functions, getting the results from a tree analysis and from a data flow analysis. The last virtual function is responsible to check which attributes belonging to this concrete analyzer. This is also a callback function which has to provided by the user. Okay, now I will give an example how a concrete analyzer, in this case a power analyzer, looks like. So the power analyzer has to sum at each hierarchy level the attached power values and to propagate it through the hierarchy. So that means this is a classical hierarchic analyzer in this case. So how the implementation looks like, that means we have to first define an attribute which has to be attached to the corresponding modules. And of course, this attribute must be derived from our base attribute I mentioned before. And then we have to implement this value function. This value function uses a value which is propagated. The value can be an arbitrary complex data item. In this case, for the power analyzers, this is simple double value which has to be propagated. And inside the value function, we simply say, okay, the previous value, or we add to the previous value the current attached value of the attribute. So that's simple, straightforward. Then, how in this case then the analyzer is implemented. Also we have to implement this callback function analyze, which describes how this analyzer should work. And then, of course, we need a function which prints, in this case, simply prints the results to a shell. And then, of course, we have to provide this isType function that this analyzer knows which attributes belonging to him. The analyze function is very simple. It's simply calling analyze hierarchy. What happens there? This method sets up the hierarchy tree and calls all value functions of the corresponding objects, and this value function summing simply up the corresponding power values. Then, okay, is type is simple. We're checking that we attaching only the power attributes to this analyzer, and this print results function accesses to the tree analyzes results. That means it gets a data structure which contains the hierarchy tree. The top level element of the hierarchy tree, the most top element, will contain the overall power in this case, and then we can go through all other elements and printing out the power. And okay, yeah. And how to use this example? The simplest way to attach attributes to modules is to doing this directly in the module description. But inside the paper, we're describing also different other possibilities, how you maybe also can attach from test benches or with utility functions attributes. But for this presentation, I will use only the simplest method. That means we instantiate and this power attribute inside our module descriptions, and in this case, inside the constructor, we say, okay, this attribute is attached to this module, and we attaching, in this case, a constant value of the power. This power value can, of course, depend from module parameter, or it can also depend from the current state of the system, so that you can have also make it dependent on the current power settings. Okay, inside the main function, how to perform the analysis is you can simply call inside the main functions. That means if you instantiate your device under test, then you maybe can run the simulation for a certain time. And if you want to do an analysis, you have to instantiate this static analyzer. You can perform the analysis, and in this case, we simply printing the results. And yeah, in this simple example, the results will be simply showing the summed up power in this case. Okay. Yeah, okay. This textual visualization comes maybe a little bit cumbersome if you have more complex systems, and that's why, especially we as a tool vendor, thought also about result visualization, and that's why our framework supports also the creation of proprietary file format, which writes out annotations we can do inside schematics. And with this framework, we are allowing then also coloring in dependency of the results, and we have also methods which then, especially for data flow analysis, to showing the signal paths. We're showing paths which have no influences to the signal paths, or paths which have influences to the signal paths but are not inside the signal paths. And maybe some examples of such annotation. In this case, it's for the power annotation. We can browse through the hierarchy and showing at each hierarchy level, of course, the global power of the whole system, then the power which the current hierarchy level has or consumes at this level. In this case, this submodule consumes 30% of the power, and then we can also show for each module, of course, which power estimation we have. We show then also the percentage for this whole module and the percentage for the whole system then. To show that it's also possible with a little bit more complex scenarios. And this is an example for noise figure analysis. Noise figure is a measure for the noise independency of the input noise. That means the classical data flow analysis, which starts at the starting point, at the source. And in this case, we run the simulation for a certain time until a control signal has, in this case, the setting 0. And if this control signal here is set to 0, the multiplexer value switch to the output 0. And you see here we colored the signal path in purple, and annotated inside the signal path then the corresponding noise figure values. And of course, for noise figure it also corresponds on the gain. That means it's we annotated also the current gain value in the signal path then. And then we run again the simulation a certain time period. The control signal changed to 1. And in this case, the multiplexer switched to a different signal path. Again, the signal path is colored in purple, and we annotated inside the signal path a noise figure. But now we have also side passes. We have this orange path, which is not inside the signal path because it's switched off at the multiplexer side, but the module is inside this orange path producing noise, and this noise is fed into the signal path. That means it influences the noise inside the signal path. That's why we colored this orange. And then we have this light blue modules, which are also producing some noise, but this noise is not fed into the signal path. This is a dead branch at the end in our signal path. Okay, this shows that you can also have more complex scenarios, and especially if you maybe have more control signals, then it's can become also interesting if you have simulated a certain period in time, and maybe you have some adaptive algorithms to see, yeah, what are the current settings. To summarize my talk, static analysis is a powerful method to estimate system properties, and especially in early design phases. If you do design space exploration, you can very quickly check different system constellations then. But it's also useful because it calculates the idle values. That means if you're doing time domain simulation and analysis, especially for more complex properties, sometimes it's very difficult to decide whether this is correct results, or maybe you have some wrong settings for your FFTs or for your measurements. And therefore, it's good for debugging to have a kind of quick analysis of the idle values you would expect in the idle case. And this is therefore also static analysis good for them. The introduced framework automatically establishes a consistency between the static analysis and the model implementation, because it's directly attached to the model structure. And what we are also supporting is that the analysis can depend on the current system state, so that you can, especially if you have control signals, that you can always check what the control setting for kind of constellation for the system properties generates then. And what I also showed, of course, the results then can be back annotated and visualized inside schematics. Okay. Thanks for listening, and do you have any questions, or how this is? Oh, no. Okay. How questions are not working, or hello?
Hey Karsten, I'm not sure who the host is, but questions can be posted in the chat box, or people can unmute and ask questions. I noticed that the session started, your talk started probably before 11 o'clock. So some people might missed the first 10 minutes or so. So there might be questions also related to that.
Yeah. The issue was the talk before was breakdown.
We've had a bit of a nightmare getting Rohit. Are there questions?
I have a question. So it seems that you use this SE attributes concept and you build something on top. Is that something which requires further discussion in standardization, or do you think this is a feature part of your offering? So where is the SC attributes good enough? Would you expect more? What's your idea about that?
Also the SC attribute from the concept is enough, because it's exactly what we need. We must attach something to the modules. And where maybe it's required to have more discussions in the standardization is exploration capabilities. The hierarchy exploration capabilities in SystemC, especially the connectivity, is difficult to explore in SystemC, especially if you have hierarchic ports. Hierarchic binding cannot be really explored in SystemC. That's very costs a lot of effort to explore it with a standard defined feature.
I think you showed a nice use case on how this could work, and indeed that you might need some better mechanisms within the SystemC standard itself.
Yeah.
Indeed to do this traversal through the hierarchy. I do know there were some changes in the SystemC API dealing with the hierarchy API. So we need to see if those changes are sufficient, or you expect more. But this might be also a topic for tomorrow for the SystemC Evolution Day.
Indeed.
Yeah.
Can I just?
Oh, sorry.
Can I just confirm whether Rohit has managed to join back in and whether you're able to talk, Rohit?
Hi, I'm here.
You are here. Okay. Before we go back to your presentation, I'd like to get your presentation back to in the same place where you stopped off. Are there any other questions for Karsten?
Yes, this is Daniel. I also have a short question.
Sure, go ahead.
Okay. So Karsten, unfortunately I missed the first 10 minutes. So my question is, did this kind of analysis you provide here, I have to, let's say, use your classes you propose, or so it's not like that you generate some code, right? No, I just...
No, we do. There's no code generation. Also, you're using the attributes and an analyzer. And what we're providing is that you can implement your own analyzer.
Okay.
That's why I had it in the motivation, especially as motivated. This was originally from RF designers, and each RF designer has his own formulas. So that's a little bit his own way of calculating properties. So it's sometimes very difficult to provide a really generalized analyzing also for a certain purpose.
Okay, no, then I fully understand it. Okay, thanks.
Hopefully the presenters will find themselves in the virtual chat rooms later, and if there are other questions, then I would recommend that you go find the presenters in the virtual